So today we're going to find the relation between angular momentum and the angular momentum about the center of mass. For that, we need to describe what center of mass is. The center of mass of a system of particle can be described as a point where all the mass of the system can be assumed to be concentrated for all the practical purposes. This makes the calculation easier because if we go to consider all the particles one by one, the calculation becomes hefty and complex. Now, in mathematical terms, let's try to define the center of mass. For that, we need a Cartesian system. Let's take a two-dimensional Cartesian system. We can also take three-dimensional, but just for simplicity, we take here two-dimensional system where this is y-axis, this is x-axis. Also, we consider here system particles. There can be a lot of particles, like say there are n particles, but for simplicity, we consider just two particles here. Let's say the mass of ith particle, this is figure 1, sorry. The mass of the ith particle is denoted by mi. So say this is particle 1 here, the mass is m1. This is particle 2, having mass m2. And let's say this is the center mass of the two particle system, okay? So let's join the masses with the origin. This is the origin of again here. We can take a lot of particles like here. This is the particle here, here. And like that we can take a lot of particles, but here we're taking just two particles because we want to keep it simple. Okay, this is the center mass. And let's say the capital R is the position vector of the center mass. Also, R1 and R2 are the position vectors of the mass m1 and m2 respectively, okay? These are the vectors. I call the position vectors of these 3 points. The position of mass m1, the center mass, and the mass m2. Now, let's say the mass of ith particle be denoted by mi. Then the center of mass of the system is given by the position vector R of the center of mass is equals sigma I mi Ri upon sigma I mi. Here, of course, the mi is the mass of the ith particle, and Ri is the position vector of the ith particle, and of course, the sigma, the summation over mi. Actually, this is m subscript I, but for convenience, we here call it mi. So this, of course, the total mass of the system, the total mass of all the particles. Like say there are n particles, so actually this equals m1 plus m2 plus plus say there are n particles. So this is total mass of the system. Okay, so we can say here that the center mass of the system can be written as I mi Ri upon the capital M. The capital M here is the total mass of the system. So well, this is the center mass of the system, and again, it can be defined as the point where all the mass of the system can be assumed to be concentrated for all the practical purposes and for all the calculation purposes.